Okay, so we're going to be dealing with the electromagnetic spectrum. I think that's the main thing that you want to think about when we're going through this is the electromagnetic spectrum. Um, and the properties that IB is going to ask about are going to be the ones that we have here. So the three, you want to see how these relate. So we have wavelength. So we want to know how these three properties interact. So wavelength, frequency, and energy. How do these three things relate? If one goes up, what happens to the other one? If one goes down, what happens to the other one? So we really want to look at that concept. Okay. So a wave, when we're talking about light, so the electromagnetic spectrum, you have a wave. So a wave could be kind of like this, where it's really long. So that'd be like a really long wavelength. So because the wavelength is the distance from the top or crest to the next top or the trough to the next trough. So either way, that's a wavelength. Now that would be kind of a long wavelength I drew there. And then you could have maybe a really short one like that. So if you compress the wave, make the wavelength small, then you're going to end up increasing the frequency. So we'll kind of look at that here in a minute. Let me clean that up a bit. Okay, so we got the wavelength definition here, distance between two crests or troughs, or two consecutive crests or troughs. But then we got this conversion. Sometimes students have trouble with this one, that a nanometer is a very small meter. So n, lowercase n, that's a nanometer. But I think you might be better just with this conversion. I actually meant to change this in the notes a few times, that 1 meter is going to equal a whole lot of nanometers. 1.0 times 10 to the ninth nanometers. So having the negative exponent is kind of hard sometimes. So I think that might be better to have the other conversion as well. So, okay, frequency. Frequency is how many of these waves go by in a certain amount of time. And that amount of time is usually a second. And so we usually measure it in a second. So you can see the unit down here, hertz. That means cycles per second. So how many cycles go by, meaning how many waves are going to go by in 1 second. And so then that is abbreviated Hz, but that stands for hertz, which is HERTZ. Okay, so that's a unit of frequency. So what we want to kind of understand is that if you stretch the wavelength out, you're not going to get a lot, the frequency is going to go down. Because if you stretch the wave out, then not many waves are going to go by in a second. But if you compress it and make it small like this, lots and lots of waves are going to go by in a second. So basically, wavelength and frequency are going to have an inverse relationship, meaning if one goes up, the other is going to go down. All right. So here's the speed of light formula. And speed of light is a constant, always the same value. And then 3.00 times 10 to the 8th meters per second. So that's not mass, that's meters. And then here's the formula where the speed of light, c, equals your frequency multiplied by your wavelength. So the other equation is the energy of a photon. And so we're talking photon, we're talking a particle of light, that the energy of photon can be determined using Planck's constant, which is right there. And then that's going to be the energy equals Planck's constant times frequency. So these are a couple of formulas that are in your data booklet. That's something that you can use on the IB exam. And so we got a couple of quick little math problems to work through. So it says the red light associated with the aurora borealis is emitted by high energy oxygen atoms. And they are at 630 nanometers. So right away, nanometers, don't want to do that. But right away, we got nanometers. And so as soon as you get nanometers, you know that they're talking about wavelength. Okay, so that's wavelength. And then it says right here, what's the frequency? So we're solving for frequency. And so Luckily, we have a nice formula for that, and that formula is right here. And so the speed of light equals frequency times wavelength. Well, we need frequency and we have wavelength, so we're good to go. So speed of light is right here. So it's going to be 3.00 times 10 to the 8th meters per second. And that's going to equal our frequency, which is going to be our x, multiplied by wavelength. Now, here's the problem, though. Our wavelength is in nanometers, and that's not going to play nice because this is in meters and this is in nanometers. So that's a problem. So we're going to need to convert those. So what I'm going to do is I'm going to use this conversion up here, right there. I'm going to use that conversion. 1 meter equals 1.0 times 10 to the 9th nanometers. So I've got 630 nanometers, and I want to get rid of them. And I want meters, so we know that 1 meter is 1.0 times 10 to the 9th nanometers. Because they're really little, there's a whole bunch of them in 1 meter, okay? So I'm going to run that through your calculator and get your unit, and that's going to be 6, I'm going to use a scientific notation, 6.300 times 10 to the negative 7th meters. And then we'll go ahead and plug that in up top and see what we get. So we'll plug in our 6.300 times 10 to the negative 7th meters there. And now you're just going to do the math, and we're going to solve for x. Okay, so x by itself. So in your calculator, 3.00 times 10 to the 8th divided by, make sure you use parentheses on this if you're using the caret, divided by 6.300 times 10 to the negative 7. And I'm going to get 4.762 times 10 to the 14th. And I don't know where I'm going to put that. I'm going to slide it up here, I think. So the answer is, and you should do this on your own calculator, don't take my word for it, 4.762 times 10 to the 14th. And that's hertz because we're looking for frequency, and that's cycles per second. Okay, so there's the answer to number 7 right there. And all those formulas are provided. You don't have to usually memorize those. Okay, so I'm going to pause it here. Finish up example 8. So I'm going to do that real quick. Example 8 is, it says a photon of light has a wavelength of 698 nanometers. How much energy does it have? Okay, so they gave us nanometers, so they gave us wavelength, but they're asking about energy. So the energy formula is right here. Energy equals Planck's constant. Energy is going to equal Planck's constant times frequency. So here's the problem. We don't have energy because that's what we're looking for. We do have Planck's constant, but we don't have frequency. So we don't have enough to solve this. So what we're going to have to do is use this formula that we used above. Speed of light equals frequency times wavelength, so we can get the frequency. So once we get the frequency, we can go ahead and dump it into that formula. Okay, so let's go ahead and do that. 3.00 times 10 to the 8th, there's a speed of light, that doesn't change, equals, we're looking for the frequency again. We have the wavelength. And so it's the same problem. It's 6.98 nanometers. So we're going to have to convert that because that's not going to be useful. So once again, use the same conversion. It'd just be, slide it over here. Going to run out of space. So it's just going to be pretty easy. 698 nanometers times 1 meter over 1.0 times 10 to the 9th nanometers. Okay, so when you run that through, you're going to get 6.98 times 10 to the negative 7th meters. So I'm just going to write that in there real quick. And now we can solve for x. X is our frequency, and so we can dump it into that energy equation. So let's run that through real quick. So it's going to be 3 to the 3.00 times 10 to the 8th, and then we're going to divide it by 6.98 to the negative 7th. And we're going to get very similar values above 4.2. It's like a 3 sig fig, so it looks like 4.297. So 4.30 times 10 to the 14th. So let's go ahead and put that in a different color. So what does this equal? That was 4.30 times 10 to the 14th. And that is our frequency. And then we're going to go ahead and plug that in right here. And so this value is going to slide in down there. Okay, so let's go ahead and do that. Clean this up a little bit because we're kind of running out of space here, but we'll fit it in. Okay, so energy, which is what we're looking for, is Planck's constant, and that's right here. That's H. So it's going to be 6.63 times 10 to the negative 34th, and that's joules per second, but you don't need that. And once again, you don't have to memorize this. This is given to you on the test. You don't have to ever memorize these numbers. And then plug in my frequency. And we're going to run this through, and we're going to get an answer in energy. And so I'm going to go 6.63 to the negative 34 times 4.3 to the 14th. You're going to get 2.85 times 10 to the negative 19th. And so I don't know where I'm going to put that. So it looks like I'm just going to maybe kind of squeeze it in up here. 2.85, not a very good looking 8. 2.85 times 10 to the negative 19th. And that is a unit of energy, so that's going to be in joules, okay? Now, it says, how much energy does it have? There you go, that's energy. If you look this up on the electromagnetic spectrum, you're going to get red light. But that's the answer to number 8 right there, okay? All right, going to pause it here, and then we'll go on to the relationship stuff about those things, which honestly is probably energy, frequency, wavelength, more likely to be on the test.